Think about the night sky. What do you see? You see stars, right? Millions of tiny distant suns. You might think you know what a star is, but the actual science is far stranger and more violent than you can imagine. We're talking about objects so powerful they can outshine an entire galaxy. We're talking about things that create every single element in your body, and we're talking about guaranteed, cataclysmic destruction. This journey is about figuring out what really makes a star, why some stars are secretly boring, and why others are basically cosmic time bombs. In this video, we're going to dive into the core of these celestial fireballs, see how they live and how they die, and uncover the unbelievable physics of their final forms, like black holes and neutron stars. We'll look at the extreme ends of the stellar spectrum, from the tiny ones that live for 1 trillion years to the massive ones that explode in a blinding flash, stick around until the end, and I'll show you why learning about the life cycle of a star is actually learning the story of your own existence. I have turned hundreds of cosmic thinkers into expert mission analyst level visionaries. But first, let's get straight to the point. What is a star at its most basic level? It's simple. A star is an object that has enough mass to generate nuclear fusion in its core. That process fusion is the only thing that separates a star from a really big hot planet. Everything else, size, color, temperature, is just a side effect of that core fusion. The life of a star begins in giant molecular clouds, massive areas of gas and dust out in space. Gravity pulls all that material together. As the cloud collapses, the center heats up. This collapsing object is called a protostar. A protostar is basically fighting a race against its own gravity. The more mass it collects, the hotter and denser its core becomes. If the core gets hot enough, about 10 million Kelvin, it hits the fusion ignition point and bam, you have a star. This new fire in the core creates outward pressure called thermal pressure, which balances the inward crush of gravity. This balance is the star's stable life, which astronomers call the main sequence. Our own sun is doing this right now. But here is where mass comes into play, and mass is the most important factor in determining a star's entire life story. We can split the universe's stars into two camps based on mass. First, you have the small mass stars, which are less than about 40% of the mass of the Sun. These are what I like to call the boring stars. Why boring? Because they burn their fuel so slowly and efficiently that they can stay on the main sequence, in that happy stable state, for nearly 1 trillion years. Think about that. The universe itself is only 13.8 billion years old. This means that none of these small stars have even had time to die yet. They haven't even used up all their fuel. Below those small stars are the absolute non-stars objects called brown dwarfs. These are protostars that simply didn't make the cut. They have less than 8% of the Sun's mass. That is the hard limit. If you fall below that line, you never start fusion in your core. A brown dwarf just keeps contracting under gravity, slowly releasing heat via a mechanism on the interior of the Sun, but it never lights up as a true star. They can hang out, warm and faintly glowing for an extremely long time. It might sound like they are not important, but these red dwarfs and brown dwarfs make up about 80% of all stars in the Milky Way. Most of the cosmos is quiet and calm, but you rarely hear about them because people like explosive endings. And that brings us to the stars we really care about. The massive stars, the ones that are destined for a spectacular death. These stars start with at least 8 times the mass of the Sun and burn through their fuel at a truly furious rate. They live short, flashy lives. While our Sun will last about 11 billion years, a massive star can race through its entire existence in just a few million years or even less. But even a star like our Sun is heading toward a guaranteed, destructive, and strange end. It's what happens when the star runs out of hydrogen fuel in its core. If mass determines how long a star lives, how much more massive does a star have to be to die 1,000 times faster than the Sun? We know the Sun is roughly 4.6 billion years old. It's been happily fusing hydrogen into helium in its core for that entire time. But here's the problem. That helium product, like ash, sinks down to the center and just sits there. It's too heavy and too cold to start fusing right away. So the helium core grows, getting denser and hotter, but remaining inert. This core is degenerate, meaning the particles are packed together in an extreme quantum state. When the Sun is about 6 1/3 billion years from now, or when it hits 11 billion years old total, it will leave the main sequence and become a subgiant star. The hydrogen fuel in the center is gone. However, there is still plenty of hydrogen available in a shell surrounding that dead helium core. The gravity from the inert core crushes that surrounding shell of hydrogen, heating it up so much that fusion ignites there instead. This is called shell burning, and it completely changes the game. Think about this. The helium core is constantly shrinking, which means the shell of burning hydrogen around it gets hotter and denser, causing the reaction rate to speed up. It's a runaway process. This massive energy boost forces the sun's outer layers to puff outward. This is the star swelling up into a red giant when the sun becomes a red giant. Its outer envelope will expand beyond the orbit of Mercury and Venus, likely swallowing Earth as well. Astronomers use huge computer simulations to model this entire process. They plug in the sun's known mass, luminosity, composition, and radius, and then they run equations of stellar structure to see exactly how these things change over billions of years. These models show that as the sun expands, its surface temperature drops, hence red. But its total brightness or luminosity increases dramatically. The sun will stay in this red giant phase for a period, until the inert helium core reaches a critical point. When it gets hot and dense enough, about 100 million Kelvin, the helium suddenly explodes in a runaway reaction called the helium flash. This flash is non-trivial. For a brief moment, the energy output of the core can be equivalent to 100 million suns. However, this energy primarily goes into lifting and expanding the stellar material around the core, so an outside observer actually sees the star's total luminosity drop sharply right after the flash. It's a temporary pause lasting only a few million years. After the helium flash, the sun will settle down and begin fusing the helium into carbon and oxygen in its core. Then, just like before, the helium fuel runs out and fusion moves to a shell surrounding the new carbon-oxygen core. This sends the sun into its final dramatic swelling known as the asymptotic giant branch, or AGB phase. During the AGB phase, the sun becomes unstable, experiencing thermal pulses, mini-explosions in the shell that happen every few thousand years. These pulses are so powerful that they begin ejecting the outer layers of the star as a fast, strong wind. For a star similar to the Sun, it might lose about 100 Earth masses of material every year for tens of thousands of years. The Earth is about 3 times 10 to the -6 solar masses. When this material is ejected, it forms a beautiful, expanding shell of gas called a planetary nebula. This sounds soft, but it is important. This is how stars enrich the universe. The material being thrown off isn't just hydrogen, it's newly created elements like carbon and nitrogen. Scientists know this because they can detect certain elements, like a radioactive element called technetium. In the stellar wind, technetium has a half-life of only 200,000 years, which is extremely short, meaning it must have been actively produced deep inside the star and recently brought to the surface before being ejected. Think about this. The carbon that makes up the DNA in your cells was made in an ancient star that died over 4.5 billion years ago. Once the outer gas layers are gone, all that is left is the exposed white-hot inert core of carbon and oxygen. This is the sun's final form, a white dwarf star. A white dwarf is incredibly dense, packing the mass of the sun into a volume about the size of Earth. It's extremely hot but tiny, so its total light output is small. Since it no longer has any fusion, it slowly cools down over time. How long do you think it takes for a white dwarf to cool off completely? The answer is, we don't know because the universe isn't old enough. The cooling phase will last for nearly 1 trillion years. Every single white dwarf ever created in the history of the universe is still a white dwarf today. That cooling core is the end of the road for our sun. But not all stars have such a quiet ending. If a star is much more massive, its death creates a flash of light so strong it can be seen across galaxies. It results in a remnant so strange that it warps space and time itself. Let's talk about the big stars now, the ones that start with at least 8 times the mass of the Sun. They live fast and die young, while the Sun takes 11 billion years just to burn hydrogen. A massive star runs through its nuclear fuel stages in a frantic race. It starts the same way, burning hydrogen into helium. But because the massive star's gravity is so strong, its core gets much hotter and denser than the Sun ever could. Once the hydrogen is gone, the star's immense gravity immediately forces the helium core to ignite into carbon and oxygen. This star keeps collapsing and igniting heavier and heavier elements. It burns carbon into neon and magnesium. It burns neon into oxygen and silicon. Eventually, the core forms an onion skin structure with shells of lighter elements fusing further out surrounding the progressively heavier elements in the center. This violent stellar existence continues until the star creates an iron core. This is the ultimate crisis for a massive star, and it is a guaranteed point of no return. Here's why. Fusion works by taking smaller nuclei and combining them into bigger ones, releasing a huge amount of binding energy in the process. This energy creates the thermal pressure that keeps the star from collapsing. If you look at a graph of binding energy per nucleon, you see a peak right around the element iron. Iron 56 is the most stable nucleus in the universe. The rules change completely here. Once the star starts creating iron, it cannot get energy from fusing iron into something heavier. That process actually consumes energy instead of releasing it. This means the star has run out of fuel. The outward thermal pressure that fought gravity suddenly vanishes. With nothing left to stop it, the iron core begins a catastrophic collapse. The collapse happens at unbelievable speed. The core, which might be the size of Earth, implodes down to a sphere only about 10 kilometers across, the size of a major city, in milliseconds. This happens faster than your brain can process a thought. The density reaches extremes, perhaps 10 billion grams per cubic centimeter. When the core material hits the ultra-dense center, it recoils in a tremendous explosion. The shockwave from this bounce starts moving outwards, smashing into the rest of the star's outer layers. This outward wave heats the surrounding material and triggers massive nuclear fusion in its wake. This single event, the explosive death of a massive star, is called a core collapse supernova, also known as a Type II supernova. Supernovae are the most luminous continuous sources of light we see in the universe. For a brief time in minutes, a supernova can outshine 1 to 10 billion suns, or even an entire galaxy of stars. Supernova explosions are complex events, and modeling them requires extremely sophisticated computer programs. Early models, which assumed the star was perfectly spherical, completely failed to produce an explosion. It took decades of work to realize that the explosion is profoundly asymmetrical. What do you think scientists see in real supernova remnants that prove these explosions are asymmetrical? Observations of supernova remnants like Cassiopeia A or Cas-A confirm this complex asymmetrical nature. The simulation must account for things like turbulence and convection driven by neutrinos. Even the initial structure of the star, how compact it was before collapse, influences the final explosion energy, the amount of radioactive elements produced, and the speed of the object left behind. The explosion pushes the star's outer material or ejecta outwards at incredible speeds, often around 20,000 kilometers per second. This ejecta acts like a bulldozer sweeping up surrounding interstellar gas. After thousands of years, the leftover debris called a supernova remnant can expand to hundreds of light years in radius. Astronomers study these remnants across all wavelengths, from X-rays to infrared, to see the heated material and the shockwaves spreading out. But the explosion isn't the whole story. What matters most is what the supernova leaves behind. That determines the two most extreme stellar objects in existence: neutron stars and black holes. When a massive star explodes, two things determine its final corpse: its starting mass and the messy, turbulent details of the collapse. If the mass of the remnant core is relatively low, say between 1.4 and 3 times the mass of the Sun, the crush of gravity is stopped by something called neutron degeneracy pressure. The resulting object is a neutron star. Neutron stars are fantastically small and dense. They are only about 10 to 20 kilometers in diameter. Yet they contain more mass than the Sun. They are so dense that a tiny teaspoon of a neutron star would weigh billions of tons. They often spin incredibly fast, some rotating 30 times a second. When a neutron star's rotation and magnetic fields align to spray beams of energy across space, we see them as pulsars. Neutron stars are closely linked to the explosion itself through tiny, almost undetectable particles, neutrinos. During the core collapse, a massive number of neutrinos are produced. These particles interact weakly with ordinary matter. Think of them as the starting gun for the entire event. Because neutrinos are produced right at the beginning of the core collapse, they arrive at Earth up to 48 hours before the light from the supernova explosion itself. To catch these early warnings, scientists use the Supernova Early Warning System, or SNEWS. SNEWS is a network of large detectors around the world, which are designed to detect the faint bursts of neutrinos. If 2 or more detectors spot a neutrino burst within 10 seconds, SNEWS alerts the world. This gives astronomers a crucial head start to point telescopes at the right spot in the sky, waiting for the light to catch up. The time between the neutrino burst and the light breaking out can give scientists critical information about the inner workings of the star right before its death. Now, back to the massive star explosion. If the core left behind is too heavy, if it measures more than 3 times the mass of the Sun, not even neutron degeneracy pressure can stop the crush of gravity. The core collapses completely, leading to the creation of a black hole. Black holes are the most extreme end product of stellar evolution. When you look at a black hole, there is no surface. What exists instead is the event horizon. What is the event horizon? Why is it that nothing, not even light, can escape the event horizon? The event horizon is the boundary around the black hole where the gravitational pull is so strong that the escape velocity, the speed you would need to travel to escape, is faster than the speed of light. Once something crosses that boundary, it is gone forever. If black holes are invisible, how do we confirm that they are really out there? We rely on observing their intense effects on the matter around them. For stellar mass black holes, we look for them in X-ray binary star systems. This is a 2-star system where a compact object, either a neutron star or a black hole, is in orbit with a normal companion star. Here's how it works. The compact object's gravity is so strong that it strips gas and material off the companion star. This material doesn't fall straight in. Instead, it spirals around the object, forming an incredibly hot, fast-rotating structure called an accretion disk. This disk gets so compressed and heated by friction that it emits huge amounts of high-energy light, particularly X-rays. In fact, these X-ray sources can emit thousands of times the total radiation of our Sun, all from an area substantially smaller than Earth. The trick to proving it's a black hole, not just a superdense neutron star, comes down to mass. Astronomers observe the companion star's orbit and calculate the mass of the invisible compact object. If the calculated mass is greater than 3 times the mass of the Sun, it must be a black hole. No known force, not even neutron degeneracy pressure, can support an object heavier than that limit. This is considered the smoking gun for a black hole. We also study supermassive black holes, which are the powerhouses at the center of galaxies. When their accretion disks are active and shining, we call the object an active galactic nucleus. The most luminous of these are known as quasars. These objects can shine as brightly as 100 billion stars, sometimes outshining the entire galaxy they inhabit. Sometimes this infalling matter doesn't just disappear. Black holes can launch incredibly powerful beams of plasma called astrophysical jets, which shoot out from the poles of the object, sometimes extending far outside the galaxy. If you want to understand space, like a NASA-level analyst quick without studying for years or paying thousands for a university degree, we have a community that will help you. Link is below. What force could possibly strong enough to power these powerful jets that stretch across galaxies? These jets, often visible in X-rays, are believed to be powered by strong magnetic fields within the accretion disk. The magnetic fields accelerate electrons and protons to extremely high speeds. These jets are so powerful they can influence the formation and evolution of the entire galaxy around them, controlling how big the galaxy can grow. This is sometimes referred to as the love-hate relationship between black holes and galaxies. So, from the smallest brown dwarfs that never light up, to the Sun, which will slowly fade as a white dwarf, to the massive stars that explode to leave behind the extreme gravity of a black hole. Mass is everything. The fate of every star is locked in that initial balance of gravity and pressure, culminating in outcomes that fill the universe with the heavy elements needed for planets, for life, and for you. Every time a star explodes, it scatters carbon, oxygen, nitrogen, and even gold across the cosmos. You are literally made of recycled star stuff. This entire discussion proves that the universe is not a peaceful place. It is a constant cycle of extreme pressure, fusion, and violent destructive power. If you are interested in how quickly things move in this powerful, chaotic universe, you need to see how long it would actually take to travel to the nearest planets and stellar systems. Click the video on the screen now for real time it takes to get to each planet and find out just how enormous the scale of space truly is. I'll see you there.